This is the third lecture of this series, EPR to quantum communication. This is part C of this series, and please go through my previous lectures on EPR paradox, quantum entanglement and Bell's theorem. So, where I discussed Bell CH/SH inequality, an average quantity which should be less than 2 or less than equal to 2 for a local realistic model, hidden variable model, and the Bell CH/SH inequality was derived under locality and reality assumptions, and it was shown under some experimental conditions the predictions of quantum mechanics can violate this inequality. For a quantum particle prepared in an entangled state like this inequality can have a value greater than 2. So, these are the expectation values with respect to this entangled state psi, and for a particular choice of measurement directions for two spin half particle for a pair of entangled particles, it can have a value of 2√2 for this entangled state. A more powerful demonstration of Bell's theorem was given by Greenberger, Horn and Zeilinger using 3 or more correlated spin half quantum particles. These are the important references for the JZ theorem. This is the theoretical paper here. So, I cannot cite all the papers related to JZ here. One can go through these papers. Unlike Bell's original theorem, JZ analysis examines perfect correlations rather than the statistical correlations or imperfect correlations, and it is independent of any inequality bound. That is why they call it Bell's theorem without inequalities. Okay, let us proceed into the JZ argument. So, here we consider a composite system consisting of 3 subsystems 1, 2 and 3, and quantum mechanics associates a Hilbert space H1 for this subsystem 1, which we consider to be a spin half quantum system. So, this is a spin half system, and this subsystem is also a spin half system, and the Hilbert space associated with this subsystem is H2. This is also spin half, and H3 is the Hilbert space, and H3 is the Hilbert space associated to this subsystem 3, which is also a spin half system, spin half two level system. And let these states up and down, up 1, we name it as up 1, and down state 1. This represent a complete set of orthonormal bases for this Hilbert space H1. Similarly, this up 2 and down 2 form an orthonormal basis for this Hilbert space H2, and this up 3 and down 3 form a complete set of orthonormal bases for this Hilbert space H3. Now, when we consider the whole system together, the quantum states for the joint system, that is this joint system 1, 2, 3 will belong, all the quantum states and operators will belong to a tensor product Hilbert space H1, tensor product H2, tensor product H3. So, this is the Hilbert space for this joint 3 qubit system. So, in this larger Hilbert space, that is in this Hilbert space, joint Hilbert space of these 3 spin half particle, we can have a complete set of orthonormal bases as follows. This is a particular choice, up 1, tensor product up 2, tensor product up 3, then we have up 1, tensor product up 2, down 3. So, this is a particular choice of 8 orthogonal state in this 3 qubit state. So, the dimension of this Hilbert space is 2 cross 2 cross 2, 8 dimension. So, we can have 8 orthonormal bases, orthonormal states like this: up up up, up up down, up down up, down up up, up down down, down down up, down up down, and down down down. So, this is a particular choice of a complete set of orthonormal bases for this 3 qubit Hilbert space. Now, in the quantum world, superposition of states are also valid quantum states. Hence, one can also prepare a superposition state for this composite system like this. Like we can take a superposition of a particular state like this or this. So we can take a particular superposition of this state or and this state, or any other superposition is also possible. But for the JZ argument or the JZ theorem, we will consider a particular state which is called the JZ state. So I am writing it explicitly here. So this is called the JZ state for this 3 qubit system. This is equal to 1 by root 2 psi JZ is equal to 1 by root 2 up 3 plus down. So this is basically a superposition state. We have taken the superposition of this state and this state, and this is called the JZ state for this 3 qubit system. This particular state, that this particular 3 qubit state, that is the JZ state, is an entangled state in this 3 qubit system. Actually this state is an entangled state. I can schematically draw in this way. So these particles 1, 2, 3, they are now correlated, and this is a particular state for this joint system which belongs to this Hilbert space H1 tensor product H2 tensor product H3, and this is an entangled state. Now let us go into the details of the JZ argument. So the JZ experiment works as follows. Suppose the 3 spin-half particles, these 3 spin-half particles are prepared in this entangled state. Then consider the following 4 mutually commuting Hermitian operators in this 3 qubit Hilbert space. So we consider 4 operators, mutually commuting Hermitian operators in this 3 qubit Hilbert space. So let us write down those operators here. Sigma x1 tensor product, sigma y2 tensor product, sigma y3, and sigma y1 tensor product, sigma y2 tensor product, sigma x3, and sigma y1 tensor product, sigma x2 tensor product, sigma y3, and the last one sigma x1 tensor product, sigma x2 tensor product, sigma x3. So these operators are associated to local spin measurement along the x and y direction. These operator, for example here, this one is associated with the local spin measurement along this. For the first particle, so sigma x1, this 1 means the spin measurement is associated with the first particle. Okay, this is the sigma y2 and sigma y3. So these operators are associated to local spin measurement on these spin half particles along this particular direction, x, or either x axis, x direction, or the y direction. And all these 4 operators commute with each other. So these 4 operators commute with each other. They are Hermitian operators, so experimentally measurable operators, and they commute with each other. Because now they commute with each other, they can have simultaneous eigenstates and eigenvalues. So these 4 operators commute with each other. They are Hermitian operators for which they can have simultaneous eigenstates and eigenvalues. And now one can actually show that this state, this psi JZ state, is an eigenstate of all these operators with the eigenvalues, particular eigenvalues. So these are the 4 mutually commuting Hermitian operator in this Hilbert space, this 3 qubit Hilbert space, and they are Hermitian. They are commuting means they commute with each other, so they can have simultaneous eigenstates and eigenvalues. And as I said, that this particular state, this JZ state, is an eigenstate of all these operators with respective eigenvalues. So one can easily verify that this particular operator acting on this jz state psi jz gives us this is equal to -1 in this state again, and this operator acting on the jz state is equal to again -1, the eigenvalue -1 and the state multiplied by the state, and this third operator acting on this jz state also gives us the eigenvalue -1 psi jz, and the last one, this operator acting on this jz state is equal to the eigenvalue here it is +1 times the state, eigenstate means jz state again. So these eigenvalue equations one can easily verify. So these eigenvalue equations one can easily verify. So for example, this one we can easily verify in this way. We know that sigma x operator, the Pauli spin operator sigma x, when act on this up state, it flips actually. So sigma x acting on the up state gives us down state. Okay, these up and down everywhere, they are the eigenstate of sigma z actually. So sigma z acting on up gives us +1 up. Z they are thus eigenstate of this operator sigma z everywhere, this up and down, -1 down. Okay, so these up and down states are the eigenstate of sigma z operator. And now if sigma x operator act on these up state, actually these are eigenstate of sigma z. I am not writing explicitly z here. So the result will be, it will flip the state. Okay, so if it is up, it will, so if it is up state, then sigma x acting on up will give us down, sigma x acting on this down state will give us up state. That Pauli spin operator you can one can easily verify with the Pauli spin operator. One can easily verify. Now if we want to verify these eigenvalue equations, then you can act this operator on this state, this psi z state. So what it will do, this operator will act on this operator will act on this, the second Hilbert space operator, this operator will act on this. So this three operator, when it will act on this part, it will flip the spins. So it will become from this it will become down down down. Okay, and this will linearly act on this part also. This operator will linearly act from left. So when this operator will act on this, they will also flip these states. This down 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 will become up up up. So after this operation, the state will become down 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 plus up up up. So basically it remains the same state with eigenvalue +1. So in this way, using the Pauli spin algebra, one can verify the other eigenvalue equations also, these equations. Okay, I wrote the eigenvalue equations for these 4 joint measurement operators here again, and we are not explicitly writing the tensor products between the operators here, but it is implicit that there are tensor product between these operators. The GIZ argument was that these quantum mechanical results given by these eigenvalue equations are incompatible with a local realistic hidden variable model. We know that the measurement outcomes of these local spin measurements, that is this sigma x1, sigma y2, sigma y3, are given by the eigenvalues of these operators sigma x1, sigma y2, sigma y3, and the eigenvalues of these operators we already know they are +1 or -1. And these spin half particles, this 1, 2, 3, they are spatially separated. Now suppose the measurement outcomes of this local spin measurement, that is sigma x1, sigma y2, sigma y3, are fixed by some local hidden variable model. Now suppose these measurement outcomes of these local spin measurement, that is sigma x1, sigma y2, sigma y3, they are fixed by some local hidden variable model. So we assign values to these operators or the observables as for sigma x1 we assign the values according to some local hidden variable model as vx1, which can take the values as +1 or -1. Sigma y2 we assign the values as, for the sigma y2 we assign the values vy2, which can also take values plus 1 or minus 1. For sigma y3 we assign values as vy3, which can also take the values plus 1 or minus 1, and these values are there for sigma x1, and these values are there, that is this vx1 vy2 whatever the value is assigned, that is there even in absence of any measurement. That is the reality concept. Also the local values vx1 of sigma x1 remains the same whether we measure sigma x or sigma y on particle 2 and 3 at a distance. That is the locality concept. So we assign predetermined fixed values according to a local hidden variable model for all these local spin measurement as follows. So the local realistic fixed values for sigma x1, the value we assign vx1, which can take the values plus 1 and minus 1. For sigma x2, the value assignment is given by this vx2 is equal to plus 1 and minus 1. For sigma x3 is local measurement, we assign the values according to a local realistic hidden variable model as vx3, which can take the values plus 1 and minus 1. Then for the local spin measurement sigma y1, we assign the values as vy1, which can take the values again plus 1 and minus 1. For sigma y2, the value assignment is given by this vy2 is equal to plus 1 and minus 1. And lastly there is the sigma y3. So sigma y3 and the value assignment is vy3, which can take the values plus 1 and minus 1. So in this way we assign the values of all these local spin observables according to a local hidden variable model. So once we fix this value, so for example here if according to a local hidden variable model, if sigma the value is fixed here, so that value will not depend on what observable we are taking here for this spin measurement for particle 2 and 3. So here if we assign this value, some particular value of sigma x1 as vx1, which can take plus 1 or minus 1, and that same value should be taken here also. Okay, so that we have to take care of. Now to reproduce these quantum mechanical results, these predetermined fixed values vx1, vx2, they should satisfy the following relations. So these predetermined fixed values, all these values must satisfy. So these predetermined fixed values must satisfy the following relations to reproduce these quantum mechanical results. So I am writing here vx1, vy2, then vy3. So these are the predetermined fixed values we have assigned according to a local realistic hidden variable model, and those values should satisfy this relation to reproduce these quantum mechanical results. So these values, multiplication of these values should be minus 1, and according to this equation the values sigma y1 vy1, vy2 and then vx3. So multiplication of these three values should be minus 1 again, and according to this third equation the value of sigma y1, that is vy1 then vx2 multiplied by vy3, this should be minus 1 again, and according to this last equation the value of sigma x1, that is vx1 then vx2 then vx3, that should be plus 1. So that should be plus 1. So these predetermined fixed values of these observable, they should satisfy these relations to reproduce these quantum mechanical results. Now from these equations we see an interesting contradiction arises, that if we multiply the values on the right hand side of these equations, the value will be minus 1 into minus 1 into minus 1 into plus 1. The right hand side value gives us minus 1, right. So, if we multiply minus 1 with minus 1 with minus 1 with plus 1, the multiplication of all these values on the right gives us minus 1, and if we multiply the values on the left hand side here, so we multiply all the values, so we multiply the values on the left hand side of these equations, clearly we can see that this Vx1 is Vx1 again, here it is Vx1, so it will be Vx1 square. We can see that here also Vy2 appears twice here and here, so it will be Vy2 square. So, in this way the multiplication of these values finally on the left hand side, if we do, we will obtain this thing Vx1 square, Vy2 square, then Vx2 square, then Vy2 square, then Vx3 square and multiplied by Vy3 square, because they appear in these equation twice actually. So, Vx1 appears here, Vx1 appears here. So, if we multiply this left hand side of these equations, then we will have this expression Vx1 whole square, Vy2 whole square, Vx2 whole square, Vy2 whole square, Vx3 square, Vy3 square. So, whatever the value according to this value assignment, we have fixed the values according to the local hidden variable model for these local spin measurement operators, and then according to this equation it gives us a value of plus 1 actually. So, this is plus 1. It is obvious because whatever the value it takes, its square will be plus 1. So, and in all this expression there are only square terms. So, finally we will have plus 1 according to the left hand side if we multiply these values, but according to right hand side the values if we multiply we are getting minus 1. So, we see we observe here a sharp contradiction coming out here. So, according to quantum mechanics, the product of these measurement outcomes, for these 4 observables should be minus 1, whereas according to these equation, according to local hidden variable model, the value assignment, the predetermined fixed values we assigned for these observables, I mean we say that these values are there even in the absence of the measurement. So, if we do that, then according to this equations we are getting a contradiction over here, very sharp contradiction we are getting, and this happens because these, I mean the local spin measurement along a particular axis appears twice in overall set of 4 product measurements. So, this is in a direct contradiction with the results of quantum mechanics. So, the GHZ experiment demonstrates the non-local nature of quantum mechanics that violates our classical intuition of local realism. Hence, these results of quantum measurement on these three spin half particles prepared in an entangled state, and the entangled state we considered this GHZ state, the state we explicitly have written earlier, and that result cannot be explained if each of these local measurement for these particles are assigned predetermined values, I mean local realistic values for these spin component before the measurement, then we arise with this contradiction. Okay. So, here it is again shown that Einstein's local realism is not obeyed by nature. So, this was the demonstration of Bell's theorem without inequalities given by Greenberger, Horn and Zeilinger. Let me make a comment here that in a recent work we discovered a temporal analog of JZ argument that establishes Bell's theorem in time without inequalities. So, one can go through that paper, the reference is given over there. Thanks for watching.
If this is the first time you are visiting my channel, please don't forget to subscribe it and tap the bell icon to get notified for my new videos. Please comment below your thoughts and suggestions would be greatly appreciated.